Next, I want to talk about what I call pass missing sets. So unlike the previous results in this section, this is something pretty new, at least to my knowledge. Menger's theorem is from the 1920s. Galay-Milgram is from 1960. You might be forgiven for thinking that everything simple enough that involves paths and digraphs has been already studied, because these are natural questions. Well, surprisingly, it is not the case. And here is an example of something that I've discovered back in 2017, which is now part of a joint preprint with two others. So, and the way I've discovered it is actually I was trying to come up with a homework problem for a previous iteration of this course. So, back in 2017, I was looking at digraphs D, again, multi-digraph to be precise, with two distinct vertices S and T selected. Inspired by the Arc-Menger theorems, I was looking at the subsets B of A that could be removed without disconnecting S from T. More precisely, without destroying all paths from S to T. So basically, you imagine you have a grid of roads, or not a grid, network of roads, and you're wondering what roads can you block, or what sets of roads can you block, while still ensuring that you can get from S to T. So I noticed I was experimenting with SageMath, but basically almost any computer language could be used here. So I noticed that the number of such subsets B seem to be even whenever D has a cycle or a useless arc. By useless, I mean an arc that is used by no path from S to T. Of course, if you have a useless arc, you can remove it or not remove it, it doesn't matter. So no wonder the number is even. But more interestingly, it's even when D has a cycle. And if not, so if you have neither a cycle nor a useless arc, then the number is odd. So I could not prove this observation. So I asked around. Fortunately, there were some number theories back at University of Minnesota when I was studying this, and very soon actually, two people helped me prove it. So soon after, Joel Brewster Lewis and Lucas Caten came up with a proof and multiple layers of generalization. The whole thing is now a joint, not really paper, but preprint at least. So I cannot fully recommend the preprint because I think the proofs are a lot less nice than they should be. And the whole thing is written up in a way that you can clearly see that we were just trying to get it on paper as fast as we could without really understanding it well. But I want to show you the theorem. So the first layer of generalization is to replace the parity claim, so evenness or oddness, by an alternating sum. And this is something you can often do, not always, but often. So this is me, Lewis, and Caten. Let T equals VA psi be a multidigraph. Let S and T be two distinct vertices of D. A subset B of A will be called path missing if there exists a path from S to T that does not use any of the arcs from in B. In other words, a path from S to T that would not be destroyed if we remove all arcs in B from A, from D. So in the terminology of lecture 27, this is the same as saying that B is not an ST arc separator. Let PM of D be the set of all path-missing subsets of A. Then we have the following. If D has an arc that is not used by any path from S to T, this is what we just called a useless arc. Then the sum over all path-missing sets of -1 to the size is 0. And therefore, the number of the sets is even. Why does this follow from this? If you haven't seen this before, this is the sum of ones and -1s. In order for it to be 0, it has to have the same number of ones and -1s. And this means that the total number of addends has to be even, which is exactly what is said here. So this is a stronger statement than this. Okay, so this part is pretty easy. The less obvious part is that if D has a cycle, then you get the same conclusion. Finally, this is again trivial. You get the same conclusion if you take, what is it? Yeah, if there are no arcs. This is basically obvious because if there are no arcs, then you cannot go from S to T, so this is empty. But finally, in all other cases, the sum equals -1 to the size of A minus the size of V prime, where V prime is the set of all vertices without degree positive. And of course, because -1 to the power of anything is odd, you see that the number of path-missing sets is odd in this case. Well, for the proof, see our preprint cited above. It's not a very fun argument. It's an induction using some kind of deletion contraction recurrence. So it's about making a graph progressively smaller and trying to move our this path-missing sets along with this. And that involves a lot of fumbling. Further levels of generality can be reached by treating this PM of D as a topological space. I don't want to go into the details, but let me say how this works briefly. PM of D is not just a random collection of sets of edges, but it is actually what is known as a simplicial complex, because any subset of a path-missing set is again path-missing subset of A. Why? Well, if you remove a bunch of arcs and you have a path, then removing a subset of these arcs also has to leave the same path. So this is a little bit better than just a random set. Simplicial complexes are known to be a combinatorial model for topological spaces. And in particular, they have homology groups, homotopy groups, and all this topological structure. Therefore, in particular, we can ask ourselves how the topological space PM of D, well, the topological space corresponding to PM of D looks like. And we have answered this in our preprint. It is homotopic to a sphere or a ball, and we know when and what dimension. So in a way, we have completely characterized the space. So I'm still trying to understand what exactly makes the theorem work, because as I said, the proof is messy. There has to be something going on behind it. I think it has to do with spanning arborescences, but it's not obvious. So think of it as a nice result or a riddle or both,